get the locus. So next we concentrate on problems on conjugate diameters and asymptotes from hyperbola. Now the first one, tangent to the ellipse cuts the circle. So that is you direct a circle. X square plus y square is equal to a square plus b square in points P and Q. Prove that CP and CQ are along the conjugate semi-diameters of the ellipse, where C is the center of the circle. So here we have got one director circle and we have got the standard ellipse. What is given is a tangent to the ellipse. Tangent to the ellipse, this one, that's the circle. So the outer one is your circle. This is your circle, and this one is your ellipse. This one is your ellipse. So what is now by keep on reading the question again and again, you will know what is what and the diagram will come out correctly. So the equation of the ellipse is this one, and the equation of the director circle is this. Equation of the tangent at theta on the ellipse. So this one is the tangent, and so any point on that, a cos theta b sin theta. So x by a cos theta plus y by b sin theta is equal to 1 is the equation of PQ. Now because PQ meets the circle NP and Q, CP and CQ will give the combined equation, and we want to show that the angle between them is 90 degrees. So if we can show that coefficient of no, we should check, wait. The equation of the tangent at theta on the ellipse is this, x by a cos theta. Now what we are going to do is, if we want to get the combined equation, we will have to homogenize the circle with the help of this line, right? So that is what is done here, x cos theta plus y by b sin theta the whole square, and then collect the coefficient of x square, collect the coefficient of y square, and the other term we are not bothered the xy term. So from here product of the roots we consider, and these things when on simplification will cancel out, leaving just b square by a square. Just leaving b square by a square. So CP and CQ are conjugate semi-diameters. We know that two lines will be conjugate diameters. So if the product gives us minus b square by a square, if the product gives minus b square by a square, then you have this. Now the next one, find the locus of point of intersection of normals at 2 points on an ellipse which are extremities of conjugate diameters. So let us say again, find the locus of point of intersection of normals at 2 points on an ellipse which are extremities of conjugate diameters. So let P and D be the extremities of a pair of conjugate diameters. So the ellipse, let P and D be the points A cos theta, B sin theta. This is known to us already. Minus A sin theta, B cos theta. Sometimes we will take it as P and Q. Here it is taken as P and D. That doesn't matter. The equation of the normal at P and Q, we can write AX by cos theta minus BY by sin theta is equal to A square minus B square. And the other one, for the other one, it is minus ax by sin theta minus by by cos theta equal to this. So adding the two, you get ax by cos theta plus by by sin theta equal to something. Now we also have cos theta. From here I will find, you get cos theta to be this, sin theta to be this, and then squaring and adding you will get the locus by dropping the suffix. So next is, if CP and CD are two semi-conjugate diameters of an ellipse, then prove that they line PD touches the ellipse. So such types of problems very simple, and they can be asked in the exam. Let the eccentric angle of P and Q be this one, that theta and 90 plus theta. Then equation of the chord PQ is, so we have the C, P and D. So if this angle is taken as theta, we know very well that the next one is pi by 2 plus theta. Pi by 2 plus theta. So let the eccentric angle of this, then the eccentric angle of D is this, the equation of the chord PD. So if I consider this, so this is a chord in a given ellipse, namely here it is taken as PQ. Now we know that the chord joining 2 points is given by x by a cos of theta plus phi, had it been phi, by 2 plus y by b sin theta plus phi by 2. It is actually so this print mistake, it should be phi. So this is the equation of the chord joining P and Q, chord PQ. So the equation of that in plus 2 itself you should have studied. Only from that we can easily get the equation of the tangent. So x by a cos of theta plus phi by 2 plus y by b sin theta plus phi by 2 is equal to cos of theta minus phi by 2. This is the equation, and we know that one is theta, the other one is phi by 2 plus theta. We just substitute that, and then this is what we get. We can cancel out one theta, so we are left with cos pi by 4, which is 1 by root 2. And so we, for the sake of convenience, what we do is we divide throughout by 1 by root 2, so that this will be a by root 2. Take it as some capital A, and the other one the same way, and b by root 2, take it as capital B, so that you will have that in this form. So in this, okay, now we have got the equation of PQ. Now go back to the problem, what we are trying to prove. We are asked to show that the line PD touches the ellipse. We are asked to show that the PD, what you have obtained, this one touches the ellipse, x square by a square plus y square by b square is equal to half. Right, now if you compare this equation with this, x square by a square, because this half comes now, so this is what you have. We are, this straight line touches the ellipse, this. So where from that we get it? See, we know that the standard form see, in general, when I am given x square by a square, see, this we have already arrived at. But what is known to us, x square by a square plus y square by b square, if that is the equation of ellipse, then the equation of the tangent is given by x by a cos theta at theta. X by a cos theta plus y by b sin theta is equal to 1. Y by b sin theta is equal to 1. So if you compare this equation with this, we have taken phi to be theta plus pi by 4. So this is what we have. So this is in this form. If any equation is of this form, with regard to this ellipse, whatever I have here, that comes here. Whatever here I have here. So this one will be tangent. So in this case we have this, so naturally it will be a tangent to the ellipse. You have x square by a square at phi, at phi. But what is phi? Phi is again um, a point. We are asked to show the PD touches the ellipse. So phi is a point on this one. Phi is a point on this one, right? So that is cos phi, a cos phi, b sin phi. So it is the equation of the tangent to that ellipse, at which point a cos phi, b sin phi. A cos phi, b sin phi. So it is in that form. So we easily conclude that the speed touches. So the technique varies here. So understand the technique, because in other cases, polar and then are some line, not only polar. So some line and that touches another curve. So both will be this. You can determine the chord, the line equation you can determine, and it is tangent to what, that will be given in the problem. But here in this problem it is not given so. You are asked to show that PD touches the ellipse. So what you do is you obtain the equation of PD and bring it to the standard form of a tangent to some ellipse, and from the way in which it is written we are able to conclude that, because we just compare, this is known to us, we just compare this with that and then conclude that this line has to touch the ellipse x square by capital A square plus y square by capital B square at a cos phi b sin phi. So you'll have to just replace capital A by root 2 and this one. So this is what you have. So it is different whenever a problem is different, and important means you put this, if it is different means put 1 star, so that you will pay extra attention when you do that particular or when you just go through that particular problem. Now the next one is a tangent to the ellipse x square by a square plus y square by b square equal to 1, whose center is C, meets the circle x square plus y square is equal to a square plus b square at q and q dash. So that CQ and CQ dash are conjugate diameters of the ellipse. Right. Now a tangent to this, any tangent to this we have, like in the case of parabola, y is equal to mx plus a by m is the equation of tangent. In the case of ellipse, we have y is equal to mx plus root of a square m square plus b square. And C is the center of the ellipse. So what is given? This tangent, a tangent to the ellipse meets the circle. So I have got a circle, direct a circle, center is 0, 0, center is 0, 0, and of course radius is root of a square plus b square. So we have any tangent to the ellipse, so something like this, this is supposed to touch. So this is the equation of this line. So what we do is we want to get a tangent to, a tangent, this is not the figure. So you need to have ellipse, you need to have an ellipse, you need to have an ellipse, a tangent to the ellipse. This is center of this is taken as C. So a tangent to this meets the director circle at what, Q and Q dash. This point is Q and this point is Q dash. So what you are trying to prove this is CQ and CQ dash are conjugate diameters. So if you are able to get the product of their slopes is minus b square by a square, then we are done. Say how to approach the problem. See, in order to get the combined, see, this is the idea. You have ellipse and you consider the tangent, and let the tangent meet the director circle at q and q dash, so that you will get cq and cp. If you can get the combined equation of this, then you will have a homogeneous equation in x and y. So it will be something like this: ax square plus 2hxy plus by square. So from which you can obtain the product of the slopes plus by square. So from this you can get the once it is homogenized, you will get combined equation from which the product of the slopes m1 and m2 can be obtained, and if you are able to show that that is minus b square by a square, then the problem will follow. So what is homogenized? The director circle is homogenized with the help of what? With the help of the tangent. Tangent to the ellipse. So the tangent to the ellipse we have taken as this. So with the help of this we are going to homogenize. So how it is done? X square plus y square is equal to a square plus b square into 1 square. And that 1 is replaced by y minus mx divided by root of a square m square plus b square. So this one is rewritten as, so that you will get 1 is equal to. And this part you must notice that it is written as a square plus b square into 1 square. So then you collect the terms containing x square, collect the term containing y square and xy term. So for convenience sake, you can further simplify this, and you rewrite in the form. Again, x square is there, y square is there, xy terms are there. Now if the individual equation Cp and Cq, we have got the combined equation. If the product of the slopes means, if m1 and m2 are roots of this equation, then product of the slopes is minus b square by a square. m1 and m2 is equal to this. So from which we can easily conclude that these two lines are conjugate diameters. So these are the problems. Find the coordinates of the ends of the diameter of the ellipse, which is conjugate to such types of problems already we have discussed. So that is not worked out. The third one we will do, fourth one, then sixth, and the last. So find the length of the semi-diameter of the ellipse conjugate to the diameter whose equation is. Such type of problems can be asked in section A, sometimes, or section B. Now we have already derived that the length of the semi-diameter conjugate to CP is given by CD is equal to root of a square sin square plus b square cos square theta. Now equation of Cp is y is equal to 3x, that is given. Now the slope of this is b by a sin theta by cos theta. So you have this, so that slope of this is equal to b sin theta by a cos theta. B sin theta by, this is b sin theta slope of Cp, difference between y coordinates divided by difference between x coordinates. So that is what you have. So from here what we get is cross multiplying 3a by b is equal to tan theta. Now this is nothing but sin theta by cos theta. So whenever this is given, it's quite natural to consider this right angle triangle and mark the sides correctly, and you can use this if this is b and this is 3a, then root of So the length of the hypotenuse we can easily get. So sine theta from the diagram, sine theta is 3a by root and cos is b by this. So that is what is done here. So that for CD, what you need to do, you'll have to substitute. Either substitute பண்ணி simplify பண்ணோம்னா we will get this. Then the next one, if x cos alpha plus y sin alpha is a chord joining the ends of conjugate semi-diameters, we are asked to show something, right? So you have an ellipse and you have the center to be say C, right? And x cos alpha plus y sin alpha equal to p is a chord joining the ends of. So we shall consider conjugate semi-diameters. Just consider the ends of the semi-conjugate diameters. Suppose I take them as say P and D, then we can easily write out the equation of P, which is done already. So this is P means this is P of theta means this is 90 plus theta. So x by a cos of theta plus y by 2 plus y by b sin theta plus y by 2 is equal to, so cos theta minus phi by 2, that is used here. So instead of phi you have theta plus phi by 2, this is what we have. And then that's further simplified, again further simplified, so that you can have x by capital A cos phi plus y by capital B sin phi is equal to 1, where AB and theta, I mean the relation between theta and phi are also given. Now we are given that x cos alpha plus y sin alpha equal to p to be a line, and another one is this, but it represents the same line, and therefore we can identify the two equations, so that you have cos alpha by cos phi by a equal to, and so on. So from this you get cos phi and you get what is sin phi. So that cos square alpha plus sin square cos square phi plus sin square phi is equal to 1 is known. So that is what is done here, and it is not a locus problem. So understand each and every problem, the technique of each and every problem that we do. Now through the foci of an ellipse, perpendiculars are drawn to a pair of conjugate diameters of an ellipse. Prove that they meet on a concentric ellipse. So the dotted one is the concentric ellipse. So this is what we are trying to prove, that P of A cos theta B sin theta at one point. Another one D is consider A 0 minus A 0, that also we consider. We consider the slope of CD, we have got it, and slope of CD as well as B cos theta A minus A sin theta. So the first one. Similarly, the slope of CP can be obtained, and that is given by minus A by B cot theta. The first one is A by B tan theta, and this is this. Now let the perpendiculars from the focus C, that is P. Okay, we should take S itself. Is y minus 0. I know a point, and I know the slope, so I can easily write out the equation of ST. Here is S and here is T, so that we can that can be easily written. Now let the perpendiculars from the focus to CP and CD meet at T of x1 y1. Let the perpendiculars from the focus so let the perpendiculars from this, from foci to CP and meet at T. So this is what we have done, the locus of which only we are trying to find, right? So similarly, the equation of s dash t is, so in the same way you consider this t of x1 y1 lies in both. So you have this. Then we'll have to simplify this further and bring it to the standard form so that we can tell that it's a concentric ellipse. So what is the meaning of concentric ellipse? The center of this as well as the center of this will be the same. So such ellipse is called a concentric ellipse. If P and D are extremities of conjugate diameters of the ellipse, show that. So there are three subdivisions. At least one subdivision can be asked in the exam. So for the first one, P and D are extremities of conjugate diameters of an ellipse. So that is standard. So that is given to you. Which one is P and D? E and D. Right. So the first one, locus of middle point of P, D. So the midpoint of this is something. So how it is proceeded? If x1, y1 is the midpoint of PD, then x1 is equal to, you want one to be a cos theta, the other one to be minus a sin theta, one to be b cos theta, the other one to be, b sin theta, the other one to be b cos theta. So we have the coordinates of the midpoint to be this. So x1 is equal to this, y1 is equal to the equation of the locus is found by eliminating theta from 1 and 2. By eliminating theta from 1 and 2, you get this. Okay, this is further simplified as this. So squaring 3 and 4 and adding, we get this. So this one. We need to get rid of this cross term, so automatically that will go by squaring and adding, and therefore the locus you can easily find. Now the eccentric angles of P and D are theta and pi by 2 plus theta. The second one, the locus of feet of the perpendiculars on PD from the center of the ellipse. The locus of foot of perpendicular on PD from the center, it is something, right? So how it is done? The eccentric angles of P and D, okay, the equation of the line joining, yes. The equation of the line perpendicular to the line PD passing through the center. So the equation of the perpendicular to the line PD equation already you have, from which you can easily obtain the slope, and you can easily get the equation of the line perpendicular to the line PD. So this is what we have. Now if x1, y1 is the foot of the perpendicular from C to PD, then it has to lie on the equation. So you have this. So from this, what is sine and cos also you will get, but that could be discussed later. Now substituting this in 1, we get this. So you have we'll have to drop the suffix to get the locus. So the third subdivision, the tangents at P and D are the locus of point intersection of the tangents at B and D. So you write out the equation of the locus at P and the equation of the tangents at P and D. So you have this. Now at the intersecting point of the two tangents in the formula, let it intersect at the point x1, y1. Then x1 by a cos theta, it will lie on the line, so it will have to satisfy the equation. So you have this.